March 18, 1879, Meriden, Connecticut. The explosion that rocked Charles Parker's foundry that morning would have convinced any reasonable engineer that American manufacturing had finally met its match. A 500-pound flywheel, spinning at 200 revolutions per minute, had torn itself apart like a bomb. 2 workers dead, 7 injured, production lines destroyed. European trade journals called it proof that American speed manufacturing was fundamentally dangerous. British engineers had calculated for decades that quality metalwork demanded individual craftsmanship, 15 years to train a master, 15 minutes to teach a factory worker. Their math seemed unassailable, yet through the wreckage and twisted steel, something extraordinary was about to emerge. Parker's immigrant workforce wasn't abandoning the flywheel press. They were rebuilding it. Because hidden in those spinning iron wheels was a manufacturing secret that would make European hand forging obsolete forever. The same mechanical principle that had just destroyed his factory was about to prove that precision could be mechanized, quality could be mass-produced, and American ingenuity could capture centuries of human skill in steel and mathematics. The morning after the explosion, Heinrich Zimmermann stood among the twisted remains of what had been America's most advanced manufacturing equipment. Shards of cast iron lay scattered across the factory floor like artillery fragments, each piece a testament to the violent forces that had torn through Parker's foundry. The main flywheel, 500 pounds of spinning death, had disintegrated at full speed, sending metal projectiles through brick walls and wooden support beams. European engineering journals would later describe it as inevitable mechanical failure, proof that American haste had finally met the immutable laws of physics. But Zimmermann saw something different in the wreckage. The German machinist knelt beside the shattered flywheel hub, running his fingers along the fractured bearing race. The failure point told a story of metal fatigue and insufficient lubrication, not flawed engineering principles. The bearing had seized first, creating catastrophic stress concentration that no cast iron wheel could survive. The fundamental concept remained sound, storing rotational energy in a massive flywheel, then releasing it through precise mechanical advantage to generate enormous pressing force. The execution had failed, not the physics. Parker found him there 3 hours later, sketching calculations in the sawdust with a piece of charcoal. The 64-year-old manufacturer looked older than his years, gray beard streaked with soot, shoulders bent under the weight of 2 deaths and 7 injuries that would haunt him forever. Insurance investigators had already declared the flywheel press too dangerous for industrial use. Workers refused to enter the building. Orders were canceling faster. Then telegraph messages could arrive from disappointed customers. "Heinrich, what are you doing?" Parker asked, his voice hollow with exhaustion and grief. Zimmermann looked up from his impromptu engineering diagram. "Calculating failure loads, Charles. This bearing," he pointed to twisted metal remnants, "rated for 12,000-pound radial load. Our flywheel generated 18,000 at full speed. Simple mathematics. We exceeded design limits." The simplicity of the explanation cut through Parker's despair like a blade. Not cosmic judgment on American manufacturing ambition. Not proof that European craftsmanship would always surpass mechanical innovation. Mathematical miscalculation that could be corrected with better bearings and stronger materials. Within days, Zimmermann had redesigned the entire system around principles he'd learned from railroad locomotives. Instead of one massive flywheel, the new design featured 4 smaller wheels, each weighing 125 pounds and spinning on precision ball bearings imported from Sweden. The distributed weight reduced stress concentration while maintaining total energy storage. More importantly, individual wheel failure couldn't destroy the entire system. The breakthrough came from Carnegie Steel Works in Pittsburgh. Andrew Carnegie's engineers had developed new alloy compositions that combined carbon steel's strength with chromium's resistance to fatigue. Where the original flywheel had been cast iron, brittle under extreme stress, the new wheels would be forged steel, capable of absorbing shock loads without catastrophic failure. Parker mortgaged his house to fund the reconstruction. European competitors, sensing weakness, flooded American markets with cheaply priced goods designed to eliminate American manufacturing permanently. British trade publications ran detailed technical analyses proving that flywheel presses represented inherently unstable technology that threatened worker safety and product quality. The mathematical arguments seemed convincing. Spinning masses stored enormous kinetic energy that could only be safely controlled through European-style individual craftsmanship. But mathematics worked both ways. Zimmermann's calculations showed that 4 steel flywheels, properly designed and maintained, could deliver 55 tons of pressing force in controlled bursts while operating safely for thousands of hours. The key insight involved energy management. Instead of releasing all stored power simultaneously, the new system would meter force delivery through precision gear trains and hydraulic dampeners. Irish immigrants Patrick O'Brien and Giuseppe Torino became the first workers brave enough to operate the rebuilt equipment. Both men had families to feed and understood that American factory wages offered opportunities unavailable in European-class systems. O'Brien had worked Birmingham's steel mills, where master craftsmen earned 5 times his wages while treating immigrant workers as expendable muscle. Torino had fled Italian poverty, where guild systems prevented advancement based on anything except family connections and decades-long apprenticeships. The new flywheel press started operation in November 1879 with elaborate safety protocols that would have seemed excessive to European observers. Emergency brake systems could stop all 4 wheels within seconds. Pressure relief valves prevented excessive force buildup. Automatic governors maintained safe rotational speeds regardless of operator input. Most importantly, the distributed flywheel design meant individual failures would trigger controlled shutdowns rather than explosive destruction. Production results exceeded even Zimmermann's optimistic projections. The rebuilt system generated identical pressing forces while reducing vibration, noise, and mechanical stress. Parts emerged with surface finishes that matched European hand forging while maintaining dimensional tolerances impossible to achieve through individual craftsmanship. Unit costs dropped to 28 cents per piece, while European equivalents sold for $2.40. More significantly, immigrant workers mastered complex operations within weeks rather than years. O'Brien learned to read pressure gauges and adjust force delivery based on material thickness. Torino developed instinctive timing for coordinating multiple flywheel releases to achieve optimal results. Their combined productivity exceeded that of master craftsmen who had trained for 15 years in European workshops. By spring 1880, Parker's rebuilt factory was producing 1,200 precision metal components daily using mechanical systems that stored human skill in steel and mathematics. European trade delegations arrived expecting to find dangerous equipment operated by untrained workers. Instead, they discovered manufacturing precision that surpassed anything achieved in Birmingham or Sheffield workshops, accomplished through American mechanical ingenuity that captured centuries of metalworking knowledge in automated processes. The flywheel press had survived its catastrophic failure to emerge stronger, safer, and more efficient than ever before. European certainty about the superiority of individual craftsmanship was beginning to crack under the weight of American mechanical achievement. By 1876, Parker's factory had become a pilgrimage site for American manufacturers seeking to understand the mathematical impossibility unfolding in Meriden, Connecticut. The rebuilt flywheel presses operated 16 hours daily, producing components with consistency that European hand forging could never achieve. Where Birmingham craftsmen might complete 15 identical pieces in a full day's work, Parker's immigrant operators generated 200 parts with dimensional tolerances measured in thousandths of an inch rather than the quarter-inch variations, typical of European handwork. The Centennial Exhibition in Philadelphia provided the stage for America's manufacturing declaration of independence. Parker transported his most advanced flywheel press to Machinery Hall, where European industrial delegations expected to find crude American contraptions suitable only for rough frontier work. Instead, they discovered a mechanical symphony of precision timing and controlled power delivery that challenged every assumption about the relationship between speed and quality in metalworking. British toolmaking representatives from Sheffield arrived with condescending attitudes shaped by centuries of industrial supremacy. They examined Parker's pressed components through jewelers' loupes, searching for the surface imperfections and dimensional inconsistencies that would prove American mechanical methods inferior to traditional European craftsmanship. The measurements they recorded defied their expectations. Surface finishes smoother than hand-polished Sheffield steel, tolerances tighter than achieved in Birmingham's finest workshops, material consistency that surpassed anything produced through individual artisan methods. Giuseppe Torino demonstrated the flywheel press operation for skeptical European observers, his movements coordinated with mechanical precision developed through months of practice. The four steel flywheels spun at calculated speeds, storing rotational energy equivalent to lifting a railroad locomotive 12 feet into the air. When Torino engaged the clutch mechanism, 55 tons of pressing force shaped raw steel billets into finished components in 3 seconds flat. The Europeans watched in stunned silence as identical parts emerged from the press, each one meeting specifications that would require hours of careful hand filing to achieve through traditional methods. The mathematical transformation was undeniable. European workshops employing master craftsmen at premium wages produced components costing $2.40 per unit. Parker's flywheel presses, operated by immigrants earning standard industrial wages, generated equivalent parts for 32 cents each. Material waste dropped from 30% in hand forging operations to less than 5% through precise mechanical control. Worker injuries declined dramatically as stored mechanical energy replaced the repetitive hammer blows that destroyed joints and caused permanent disabilities in traditional blacksmithing. Heinrich Zimmermann's engineering innovations attracted attention from unexpected quarters. Railroad manufacturers recognized that flywheel pressing could produce locomotive components with strength characteristics superior to traditional forging methods. The controlled force delivery created grain structures in steel that enhanced durability while reducing weight. Coupling hardware pressed through flywheel systems demonstrated fatigue resistance that exceeded hand-forged equivalents by measurable margins. More importantly, the speed advantage enabled American manufacturers to respond to market demands with unprecedented agility. European craftsmen required weeks to complete custom orders, their production schedules constrained by the sequential nature of individual workmanship. Parker's factory could retool flywheel presses for different component specifications within hours, switching from railroad hardware to agricultural implements to firearms components based on fluctuating demand patterns. The success attracted immigrant workers from across Europe, men who understood that American mechanical systems offered advancement opportunities unavailable in traditional guild structures. Patrick O'Brien brought his cousin Seamus from County Cork, teaching him flywheel operations that generated wages comparable to master craftsmen while requiring weeks rather than years of training. Italian families arrived from villages where metalworking remained locked within hereditary craft traditions that prevented social mobility regardless of individual skill or ambition. Parker's workforce grew to 340 employees by 1877, representing a microcosm of American industrial democracy. German precision combined with Irish determination and Italian innovation, creating collaborative problem-solving approaches that improved production efficiency through shared insights. Workers suggested mechanical modifications that increased flywheel effectiveness, developed maintenance procedures that extended equipment life, and invented quality control methods that surpassed European workshop standards. The financial transformation validated every risk Parker had taken in pursuing mechanical innovation over traditional methods. Monthly production reached 50,000 precision components, generating revenues that exceeded European competition while maintaining profit margins impossible to achieve through handcrafting approaches. The factory that had nearly bankrupted him in 1879 now employed entire immigrant neighborhoods and contributed substantially to Connecticut's industrial economy. European response shifted from condescension to alarm as American mechanical products invaded markets previously dominated by traditional craftsmanship. British hardware exports to America declined by 40% between 1876 and 1878 as domestic flywheel production satisfied demand at lower costs and higher quality. German toolmakers found their premium-priced products competing against American alternatives that matched precision while offering significant price advantages. The ultimate validation came from an unexpected source. Annie Oakley, America's premier exhibition shooter, chose Parker Brothers shotguns manufactured using flywheel press components over European firearms costing 3 times as much. Her endorsement carried weight beyond marketing value. Professional shooters demanded absolute reliability and precision that could only be achieved through consistent manufacturing processes. European sporting magazines reluctantly acknowledged that American mechanical methods had achieved quality standards matching the finest London gun-making traditions. By 1878, Parker's flywheel presses had proven that precision could be mechanized, efficiency could be systematized, and quality could be mass-produced through American mechanical ingenuity. The mathematical impossibility had become industrial reality, transforming immigrant workers into skilled operators while challenging European assumptions about the relationship between speed, cost, and manufacturing excellence. The factory floor hummed with mechanical precision that stored centuries of metalworking knowledge in steel and mathematics, making craftsmanship available to anyone willing to learn rather than privileged few born into traditional guild systems. The second explosion came without warning on March 15, 1879, during the peak production shift when all 4 flywheel presses operated simultaneously to meet spring orders from railroad companies across the expanding American West. Heinrich Zimmermann was reviewing production schedules in his office when the factory floor erupted in a thunderclap of shattering steel and screaming metal that shook the entire building. The rebuilt flywheel system that had operated flawlessly for 4 months suddenly became a weapon of mass destruction, turning precision manufacturing equipment into deadly projectiles that carved through brick walls and wooden support beams. The primary flywheel on press number 3 had suffered catastrophic bearing failure, while spinning at full operational speed of 200 revolutions per minute. Unlike the controlled shutdown system Zimmermann had designed, this failure occurred so rapidly that safety mechanisms couldn't respond fast enough to prevent disaster. The 125-pound steel wheel disintegrated under centrifugal forces that exceeded the material's tensile strength, sending fragments through the factory like artillery shells. Secondary explosions followed as flying debris destroyed steam lines and damaged neighboring equipment, creating a chain reaction of mechanical destruction. Giuseppe Torino died instantly when a flywheel fragment struck him while he operated press number 2. The Italian immigrant who had learned precision manufacturing in weeks rather than years became the victim of the mechanical system that had promised to democratize skilled labor. Patrick O'Brien survived the initial explosion but suffered massive internal injuries from flying steel that would claim his life 3 days later in Hartford Hospital. 7 other workers sustained injuries ranging from broken bones to severe lacerations, their bodies bearing witness to the violent forces unleashed when stored rotational energy escaped mechanical control. Parker arrived at the factory within minutes of the explosion to find his life's work transformed into a scene of carnage and twisted metal. The production floor resembled a battlefield where mechanical innovation had warred against the laws of physics and lost decisively. Insurance investigators would later calculate that the primary flywheel had released energy equivalent to a dynamite blast, concentrating decades of stored rotational force into milliseconds of devastating destruction. The mathematical precision that had made American manufacturing competitive with European craftsmanship had become a precise instrument of death. European trade publications seized the disaster as vindication of their long-standing criticisms regarding American manufacturing methods. The London Engineering Review published a detailed technical analysis proving that flywheel systems represented inherently unstable technology that prioritized production speed over worker safety. British experts calculated that spinning masses storing such enormous kinetic energy could never be safely controlled through mechanical systems, regardless of engineering sophistication or safety protocols. The article concluded that American industrial ambition had finally collided with immutable physical laws that European craftsmen had respected for centuries. The Birmingham Industrial Association issued an official statement declaring the Parker factory explosion as proof that quality manufacturing demanded individual craftsmanship rather than mechanical automation. Master craftsmen working at traditional forges might produce fewer components per day, but they operated within natural human limitations that prevented catastrophic failures. European workshops had never experienced accidents involving stored rotational energy because they relied on human muscle power applied through hand tools rather than mechanical systems that concentrated dangerous forces beyond safe control limits. Insurance companies responded with mathematical certainty, refusing coverage for any American manufacturer operating flywheel presses or similar energy storage systems. Actuarial calculations demonstrated that potential losses from mechanical failures exceeded any reasonable premium structure, making flywheel technology essentially uninsurable under existing risk assessment models. Lloyd's of London published new industrial policies specifically excluding coverage for American mechanical presses, effectively declaring such equipment too dangerous for commercial operation. Workers throughout Connecticut's manufacturing region refused to operate flywheel systems, spreading word through immigrant communities that American mechanical innovation had proven fatally dangerous. Skilled operators who had learned precision manufacturing through Parker's training programs sought employment in traditional workshops where human limitations provided inherent safety constraints. The Irish and Italian families who had found economic advancement through mechanical operations now viewed flywheel presses as death traps disguised as manufacturing equipment. Orders canceled faster than telegraph messages could reach Parker's office as customers learned of the explosion through newspaper accounts that emphasized the violent nature of mechanical failure. Railroad companies that had relied on Parker's precision components switched to European suppliers despite higher costs and longer delivery schedules. The mathematical advantages of flywheel pressing meant nothing if equipment could explode without warning, transforming manufacturing facilities into potential battlefields where workers faced mortal danger from the machines they operated. The financial impact threatened Parker's entire industrial empire. Monthly production dropped to zero as the factory remained closed pending investigation by state industrial safety officials. Fixed costs continued accumulating while revenue disappeared completely, forcing Parker to mortgage personal property to maintain payroll for workers who couldn't safely return to their jobs. European competitors flooded American markets with products priced to eliminate domestic manufacturing permanently, sensing an opportunity to destroy American mechanical innovation through economic warfare. Heinrich Zimmermann spent sleepless nights analyzing the technical failure, searching for engineering solutions that could restore safety to flywheel operations. His calculations revealed metal fatigue patterns in bearing races that had developed gradually over months of high-speed operation. The Swedish ball bearings that had seemed adequate for railroad applications proved insufficient for the sustained rotational loads generated by industrial flywheel systems. Microscopic wear patterns had accumulated until bearing failure became inevitable, creating catastrophic consequences when mechanical control systems lost effectiveness. By summer 1879, the factory that had employed 340 workers producing 50,000 precision components monthly stood silent and empty. European trade journals declared American mechanical manufacturing a brilliant failure, too dangerous for sustained operation and too unreliable for industrial applications requiring consistent quality. The flywheel press appeared destined for history's catalog of promising innovations that failed to survive contact with practical reality, leaving American manufacturers dependent on European craftsmanship for precision metalworking components. Heinrich Zimmermann refused to accept that mechanical precision had reached its physical limits. Through the autumn of 1879, while European competitors celebrated the apparent death of American flywheel technology, the German engineer worked 18-hour days redesigning every component that had contributed to the catastrophic failure. His breakthrough came from studying locomotive disasters on the Pennsylvania Railroad, where mechanical failures had taught engineers that distributed systems survived stresses that destroyed concentrated mechanisms. The revolutionary insight involved abandoning the concept of massive energy storage in favor of modular power distribution. Instead of 4 large flywheels storing dangerous amounts of kinetic energy, Zimmermann designed 12 smaller wheels, each weighing 42 pounds and spinning at precisely calculated speeds to deliver equivalent pressing force through coordinated timing. The mathematics proved elegant. 12 wheels storing smaller energy quantities could generate identical mechanical advantage while eliminating the catastrophic failure potential that had destroyed the previous system. Carnegie Steelworks provided the metallurgical solution through newly developed chromium-vanadium alloys that combined unprecedented strength with fatigue resistance. Andrew Carnegie's engineers had discovered that adding precise quantities of vanadium to steel created molecular structures capable of withstanding repeated stress cycles that would fracture conventional materials. The new flywheel wheels, forged from this advanced alloy, could operate at higher rotational speeds while maintaining safety margins impossible to achieve with earlier steel compositions. Parker mortgaged his Connecticut estate and borrowed against future production to fund the complete factory reconstruction. European observers interpreted his financial commitment as desperate American stubbornness, refusing to acknowledge that mechanical innovation had reached its practical limits. British trade publications ran detailed analyses proving that distributed flywheel systems would simply create multiple failure points, multiplying rather than reducing catastrophic risk potential. The mathematical logic seemed unassailable. More mechanical components meant more opportunities for dangerous breakdowns. The rebuilt system incorporated safety innovations that addressed every failure mode identified in the March disaster. Emergency brake systems could stop all 12 flywheels within 4 seconds through electromagnetic clutches that activated automatically when sensors detected abnormal vibration patterns. Pressure relief valves prevented force buildup beyond predetermined limits, while mechanical governors maintained rotational speeds within narrow bands, regardless of operator input variations. Most importantly, individual wheel failures triggered immediate shutdown of neighboring units, preventing the cascade effects that had amplified the original explosion. Giuseppe Torino's younger brother, Marco, became the first worker brave enough to operate the rebuilt equipment, driven by family financial necessity and determination to honor his brother's memory through successful mechanical operation. The 23-year-old Italian immigrant understood that American factory wages offered opportunities unavailable in European class systems, despite the risks involved in operating experimental manufacturing technology. His steady nerves and mechanical intuition made him ideal for testing systems that combined unprecedented power with unproven safety mechanisms. The new flywheel configuration delivered superior results from its first operational day in January 1880. Distributed energy storage eliminated the violent vibrations that had characterized earlier systems, while coordinated wheel timing produced pressing forces with precision that exceeded European hand-forging capabilities. Components emerged with surface finishes smoother than achieved through traditional methods, dimensional tolerances measured in 10,000ths of an inch, and material consistency that surpassed anything produced in Birmingham or Sheffield workshops. Production capacity doubled while safety improved dramatically through engineering innovations that captured mechanical lessons from locomotive and steamship industries. The 12-wheel system generated 68 tons of controlled pressing force, while operating with noise levels substantially lower than the previous configuration. Worker training periods shortened as distributed controls proved more intuitive than the complex timing required by earlier flywheel designs. Marco Torino mastered advanced operations within 3 weeks, achieving productivity levels that would require months of traditional apprenticeship in European workshops. Patrick O'Brien's cousin Seamus emerged as the system's most skilled operator, developing instinctive timing for coordinating multiple wheel releases to achieve optimal results for different materials and component specifications. His innovations included pressure variations that enhanced grain structure in steel components, cooling sequences that improved material properties, and quality control methods that identified potential defects before they affected production batches. European-trained craftsmen visiting the factory admitted privately that such precision exceeded anything achievable through individual workmanship, regardless of skill level or experience duration. By spring 1880, Parker's reconstructed factory was producing 1,500 precision components daily using mechanical systems that had evolved beyond their catastrophic origins into manufacturing technology of unprecedented sophistication. The mathematical impossibility had become industrial reality through American engineering persistence that refused to accept European conclusions about the fundamental limitations of mechanical innovation. Insurance companies reluctantly provided coverage after witnessing months of safe operation that generated accident rates lower than traditional manufacturing methods. European response shifted from celebration to alarm as American mechanical products again invaded markets previously reclaimed by traditional craftsmanship. British hardware manufacturers found their premium-priced goods competing against American alternatives that matched precision while offering substantial cost advantages. German toolmakers discovered that their carefully protected guild methods could not compete with mechanical systems that democratized precision manufacturing while maintaining quality standards impossible to achieve through individual artisan approaches. The ultimate validation came through international recognition at industrial exhibitions across Europe, where American mechanical precision earned reluctant acknowledgement from traditional craftsmen who had dismissed flywheel technology as inherently flawed. Birmingham master craftsmen examined Parker's pressed components through precision measuring instruments, searching unsuccessfully for the surface imperfections and dimensional inconsistencies that would prove mechanical methods inferior to hand-forging approaches. Their measurements confirmed mathematical superiority that challenged fundamental assumptions about the relationship between individual skill and manufacturing quality. Worker confidence returned as months of safe operation proved that mechanical precision could be achieved without sacrificing human safety. Immigrant families throughout Connecticut sought employment at Parker's factory, recognizing that American flywheel technology offered advancement opportunities while providing safer working conditions than traditional metalworking methods. The reconstructed system had not merely survived its catastrophic failure, but emerged as manufacturing technology that surpassed European craftsmanship through mechanical innovations that stored centuries of metalworking knowledge in steel and mathematics accessible to anyone willing to learn. By 1885, Parker's flywheel presses had transformed from experimental American contraptions into manufacturing technology that European industrialists studied with grudging respect and growing alarm. The factory in Meriden, Connecticut employed 180 workers operating 12 precision flywheel systems that produced 200,000 metal components annually with quality standards that surpassed traditional European craftsmanship. The mathematical transformation was undeniable. Equivalent production through hand forging would require 3,000 master craftsmen at 5 times the operating cost. European manufacturers faced an impossible choice between abandoning centuries of guild traditions or accepting competitive obsolescence in global markets, increasingly dominated by American mechanical precision. Birmingham toolmakers dispatched technical delegations to Connecticut, ostensibly to investigate American manufacturing methods, but actually to acquire flywheel technology that threatened British industrial supremacy. The visitors arrived expecting to find crude mechanical systems operated by untrained workers, instead discovering manufacturing sophistication that exceeded anything achieved in European workshops through individual craftsmanship. Heinrich Zimmermann had become an unlikely celebrity in international engineering circles. His distributed flywheel design, studied in technical schools from London to Berlin, as an example of American mechanical innovation that solved complex engineering problems through systematic analysis rather than traditional methods. European universities invited him to lecture on energy storage principles, seeking to understand how immigrant mechanics had achieved precision manufacturing that surpassed results from craftsmen trained through 15-year apprenticeships in established guild systems. The financial impact extended far beyond Parker's individual success. American mechanical hardware dominated world markets as flywheel-pressed components offered superior quality at lower prices than European alternatives. Railroad expansion across the American West depended on Connecticut-manufactured coupling hardware that demonstrated fatigue resistance impossible to achieve through hand-forging methods. Agricultural implements pressed through flywheel systems proved more durable than traditional European tools while costing significantly less to produce and purchase. Marco Torino had evolved from nervous immigrant worker into master instructor, who trained new operators in flywheel techniques that democratized precision manufacturing. His teaching methods combined Italian mechanical intuition with American systematic efficiency, enabling recent immigrants to master complex operations within weeks, rather than the years required for traditional metalworking apprenticeships. European observers noted with concern that American factories were producing skilled workers faster than European guild systems could train replacement craftsmen. the psychological transformation proved as significant as the mechanical achievements. American workers approached manufacturing with confidence born from operating systems that amplified human capability rather than replacing it entirely. Flywheel presses required skill, timing, and mechanical understanding, but these abilities could be learned through practice rather than inherited through family traditions or purchased through lengthy apprenticeships. The democratic implications threatened European social structures based on craft exclusivity and hereditary advantages. Seamus O'Brien had developed innovations that pushed flywheel technology beyond its original parameters, discovering that coordinated wheel timing could achieve surface finishes superior to hand polishing while maintaining dimensional tolerances measured in thousandths of an inch. His modifications attracted attention from precision instrument manufacturers, who required accuracy levels previously achievable only through expensive individual craftsmanship. American mechanical systems were approaching precision limits that European hand methods could never match consistently. European governments responded to American manufacturing competition through protective tariffs designed to preserve domestic craft industries from mechanical obsolescence. British Parliament debated restrictions on American hardware imports, while German states imposed duties that doubled the price of Connecticut-manufactured goods. The economic warfare reflected deeper concerns about social disruption that would result from mechanical systems eliminating traditional craft employment throughout European industrial regions. Parker Brothers Firearms demonstrated the ultimate vindication of American flywheel technology through international recognition that transcended national prejudices. European sporting magazines reluctantly acknowledged that Connecticut-manufactured shotguns matched London gun-making standards, while offering superior consistency and lower costs. Annie Oakley's continued endorsement of Parker weapons provided credible testimony that American mechanical precision had achieved quality levels demanded by professional marksmen who staked their reputations on equipment reliability. The technological diffusion accelerated as American manufacturing success attracted European investment and immigration. British entrepreneurs established licensing agreements to produce flywheel presses in Birmingham workshops, while German industrialists hired American engineers to install mechanical systems in traditional metalworking facilities. The irony was unmistakable. European capital was funding the mechanization that would eliminate European craft advantages through systematic application of American engineering principles. Worker productivity reached levels that defied European calculations about the relationship between individual skill and manufacturing output. Parker's factory achieved per capita production rates that exceeded European workshops by factors of 10 or more, while maintaining quality standards impossible to achieve through traditional methods. The mathematical advantage extended beyond simple quantity comparisons to encompass precision, consistency, and reliability metrics that demonstrated mechanical superiority across multiple performance categories. By 1885, the flywheel press had proven that American mechanical ingenuity could capture centuries of European craftsmanship knowledge in steel and mathematics accessible to immigrant workers willing to learn systematic methods. The success extended beyond individual economic achievement to represent democratic manufacturing that offered advancement opportunities based on ability rather than birth circumstances or guild membership. European observers recognized that American industrial methods threatened not merely craft traditions, but social structures based on hereditary skill transmission and craft exclusivity. Charles Parker surveyed his transformed factory with satisfaction earned through decades of risk-taking that had validated American mechanical innovation against European skepticism. The 69-year-old manufacturer had proven that precision could be mechanized, quality could be systematized, and manufacturing excellence could be achieved through democratic methods that made advanced capabilities available to anyone willing to master systematic techniques. The flywheel press represented more than technological achievement. It embodied American principles that individual determination and mechanical innovation could overcome traditional limitations imposed by class structures and inherited advantages. The Industrial Revolution had reached its democratic phase, where mechanical systems amplified human capability rather than replacing it entirely, creating manufacturing processes that combined the best aspects of individual skill with the consistency and precision possible only through systematic mechanical methods.